Welcome to What Physicists Do. Today's speaker is Dr. Joel Fajans from UC Berkeley, which I knew he had been come to the series before, but we were trying to track down when, and there was a memory of he coming with his wife, Karen, who's in the audience today, and it didn't make sense because it was 91. Well, he was here in 99 as well. So, so by 99 he had met Karen, so they came up together. So he's familiar with the area. For those of you who are wondering, we are going out to dinner with the speaker. Come up and talk to me afterwards if you'd like to join us. But I've been endeavoring to get him to come to the series for a while now. I wasn't here in 99 or 91, but his recent work, he's well known and well respected in plasma physics and fluid dynamics, but his recent work on trapping antimatter hydrogen, or antihydrogen, antimatter atoms, as opposed to the antimatter particles, which have these very, very short lives in collider type events. The idea of capturing them in the atomic state it was profoundly interesting to me. He's going to give a broad talk on the basis of his work, and I think that it's going to hit the right level for all of us here, but I'm very interested in this anti-hydrogen atoms. So I've asked him, and he was good enough to join us. He has his bachelor's and his PhD from MIT. He went to UC San Diego for his postdoc before joining the faculty at Berkeley. He was a Miller Fellow. He's been an NSF Presidential Young Investigator, a very prestigious award. He's been a young investigator from the Office of Naval Research, and he's a Fellow of the American Physical Society and a Sloan Fellow. We are very honored to have Dr. Joel Fajans speaking today.
Thank you very much for having me here. You might have noticed many of those awards were for when I was young, and I'm not so young. As a matter of fact, I came up here, the first time my wife came up here with me was at the beginning of our marriage. She's up here now, and I hope this isn't marking the end of our, never mind. But in any case, I'm very pleased to be here to talk about antihydrogen atoms and how we trap them and study them, but also I'm going to actually spend a good part of my talk on the motivation for these studies, in addition to how eventually getting to how we actually go about doing this. This is I work as in part the Alpha collaboration. This is a rather exhaustive list. Some of these people were students, like this is an undergraduate student who did some very significant work about the way our experiment was ultimately designed. And have departed. We're about 40 people on the average day. So to begin, I'm sure you all know that it was Benjamin Franklin who first postulated that there are negative and positive charges that we've now know are identified by the negative charge being on an electron and the positive charge being on a proton. And you put those things together, of course, and you get a hydrogen atom. I apologize for the grade school model of a hydrogen atom, which I'm not even supposed to show, but actually it works very well for our purposes, so we're going to leave that. I'm going to continue to refer to that. So these are the standard particles that we have in life. There's a periodic table on the next wall, but there are other particles, like for instance, there's the positron, and in a series of papers in the late 20s or so, Dirac predicted on the basis of the Dirac equation, this equation over here, that there would be a particle that was almost the same as an electron, except that instead of being negatively charged, it would be positively charged. And aside from the change in the sign, positrons are thought to be otherwise identical to electrons. Now, it didn't take long for Carl Anderson to find these positrons. This is a trace of a positron going through a cloud chamber in 1932. These were in cosmic ray experiments. Why cosmic rays? Well, as I'm sure you know, I'm sorry, I'm having trouble with this thing, getting used to this thing. As I'm sure you know, at the top of our atmosphere is being constantly bombarded by energetic particles like protons, for instance. And when they hit other nuclei, like an oxygen nuclei, they tend to cause a shower of particles. Many of those particles are muons, which ultimately come through us. As you sit in the audience here, there's some 1 to 10 muons per second, I think it is, going through your body at every instant. But some of those particles are actually positrons. And there can be an enormous number of these positrons because when you have an energetic particle come in, it really showers like crazy, as is represented in this picture of what might actually happen. So Anderson had no trouble detecting positrons there. These days, we typically find positrons in other ways. For instance, here's a banana. And if I was to finish eating this banana, banana has potassium-40 in it. And potassium-40 is a radioactive element of isotope of potassium. So if I was to finish eating this, I would ingest quite a bit of potassium-40. And not all the time, actually relatively rarely, but occasionally when potassium-40 decays, it decays emitting a positron. So as a result of my eating that banana before the potassium in that banana got excreted out of my system, the potassium that I ingested in that banana would result in about 100 positrons being generated within my own body. And of course, there's lots of potassium in you. I mean, you don't have to eat bananas to get potassium. So all of you have far more potassium in you than would come from just a single banana. So there's actually quite a bit of antimatter being generated inside of you on a radioactive basis. There are artificial positron sources which are made at accelerator labs by transmutation of formally stable elements. The most important one is sodium-22, which is a very, very intense source of positrons. It's used, for instance, in PET scans. Sorry, I keep on screwing up here. PET scans are revolutionizing medicine these days, and also here's, for instance, some poor person who has a cancerous liver, I think it is, which is being imaged by the positrons. But the advantage of PET scans over previous technologies is that the positrons tend to be emitted from regions of your body which are metabolically active. So you can, for instance, tell what somebody is thinking, supposedly, by having them ingest something that emits positrons, which gets absorbed into the metabolically active regions. So it's a somewhat scary technology, but we use these things because it's such an intense source that it's actually a great source of positrons for our experiments, those positrons that will ultimately make into antihydrogen atoms. Now, in addition to antimatter electrons, or these positrons, there are also antiprotons. These are simply protons which have an inversion of the sign of their charge. So instead of being positively charged, an antiproton is negatively charged. And just like with electrons and positrons, aside from the change in charge, antiprotons are thought to be otherwise identical to protons. Antiprotons were actually first made in Berkeley, so not very far from here, in 1955 by Segre and Chamberlain. Chamberlain is the tall one and Segre is the short one. They both got the Nobel Prize for this. And in fact, antiprotons are still made at CERN in almost the same way that they were made in Berkeley a long time back. Here's a picture of the CERN ring. This is the 17-mile now LHC ring, which goes through what used to be the French and Swiss countryside and is now mostly, sadly, built up housing developments, but never mind that. There used to be cows, not houses here. And the AD, the facility that we use where the antiprotons are generated, is a tiny little thing sitting right over here. It's about 100 meters in diameter compared to this being about 5 miles. So it's a tiny thing, a tiny ring, which decelerates the antiprotons after they've made. A little bit more about that later. But that brings us to the question of what's so special about antimatter. I mean, why do we care? So the sign is different, but does it do anything that's interesting? And the one thing that it does that it's interesting, or the most obvious thing that it does that it's interesting, is that when antimatter touches matter, it blows up in a rather large explosion. All of the mass of the matter and the antimatter gets converted into energy through Einstein's famous equation, E is equal to mc squared, which makes antimatter an extremely powerful explosive. Some of you may have had the misfortune to have seen the movie Angels and Demons, or perhaps read the book. And in that book, about 1/4 gram of antimatter was stolen from a research lab at CERN. Actually, basically the project that I'm working on now is the basis of this book, though I was not working on the project when Dan Brown wrote that book. But anyway, 1/4 gram is equivalent to 10 grains of rice, so not very much. And some people might think it's implausible that that could make a large explosion, but in fact, it would make about a 10 kiloton explosion. For a reference point, the bomb that was used on Hiroshima was 15 kilotons, so it's only slightly bigger, but it was made from 64 kilograms of uranium, not all of which actually fissioned, but never mind. You can see that this is enormously more explosive than normal matter would be. Yes?
So matter and antimatter both have positive matter? I mean, mass is positive mass?
Yes, inertially they certainly both have positive mass. Yes?
And would it spin, if there were an antihydrogen, would it rotate the other direction? From the North Pole?
Okay, so now I'm getting into trouble having put up that orbital model.
Okay.
Hydrogen atom, where you can think about things going around. Of course, the ground state of any atom is a spherically symmetric shell with no obvious orbitals going around inside. But there is an issue about spins, which I'll come to later on in the talk. So, some people actually have worried about whether or not this research could be used to make a bomb. And actually, there's nothing to worry about here. Antiprotons are still made in exactly the same fashion, basically, as they were made at CERN, at Berkeley in 1955, by crashing very energetic protons into a metal. And this is an extremely inefficient process. Only about one proton in a million is turned into an antiproton. And this is a fundamental physics limit, not a technology limit, so it's not likely to get all that much better. People have calculated that to make about 1 gram of antimatter would require the world's entire energy production for 1,000 years. Except some people have calculated that this would actually be 100,000 years. So the dispute isn't going lower, it's more going on the upper side. So there's sadly, or beneficially, I should say, no prospect for us getting macroscopic quantities of antimatter, which is the sad part about this. And I promised somebody to show them a warp drive. Here's my warp drive here. The sad part about this is that if we did have copious quantities, or macroscopic quantities even, of antimatter, it would be easy for us to build rocket ships that could explore the stars. About this much, a fist's worth of antimatter would be sufficient to send a rocket ship to the nearest, a near star in a fairly short period of time, which is absolutely amazing to contemplate. And you wouldn't need much more to send. I went backwards. I'm not having any luck with this thing.
Does anyone have just a
no, it's fun. I'll get used to it, I'm sure. But anyway. It wouldn't take that much more to send a real spaceship, say something the size of a 747, to a star. But it's not going to happen. So aside from the sign swaps, antimatter is thought to be otherwise identical to matter, which brings us to the question of why bother to study antimatter. Annihilation is fun, but you do that a couple of times and you're bored. So why bother to continue to study this? Well, one reason is, well, let's face it, annihilation is just plain fun. But aside from all of the science fiction aspects of this, the real reason to bother is that we exist because there is almost no antimatter in the universe. And if there was a lot of antimatter in the universe, we likely wouldn't exist because we would just annihilate on that antimatter. And this is a big puzzle. In fact, there have been poems written in the New Yorker about it, about this problem. I mean, referring to things like macassars. Some of you who are older might know what an antimacassar is. So an anti-antimacassar is a macassar. Never mind. But we really know that there's not a lot of antimatter in the universe. We know it in several different ways. One is that when positrons annihilate on electrons, they make very characteristic radiation, which is easy to detect and distinguish. And we see very, very little of this characteristic radiation out there in the universe. So there's not a lot of positron and electron annihilation going on. Furthermore, cosmic rays come from come from very far away. They don't come from the solar system. Most people might think that cosmic rays come from our sun or even nearby suns. They don't. They come from other galaxies. And so we have a good probe of what those other galaxies are made out of, and we essentially detect no antimatter in the cosmic rays. So there's really good evidence that there aren't any antimatter stars out there, no antimatter galaxies. So the question then becomes, why is that? Because every accepted theory of the Big Bang at this point says that when the Big Bang happened 14 billion years ago, equal amounts of matter and antimatter were created. And if equal amounts of matter and antimatter were created, then everything should have annihilated, and nothing should have been left behind. But we know that we're here. So at least a little bit did not mutually annihilate, leaving us behind. So how could this have happened? The only way to explain this is that somehow or other the Big Bang produced just slightly more matter than it did antimatter. And really, though, there are some mechanisms that people have come up with for very, very slight differences between the matter and antimatter production in the Big Bang. Nobody has any accepted theory as to how you could get a difference which is this large. Now, admittedly, this doesn't look large, but it is large compared to what the theorists say about these sorts of things. I'm sorry?
We won, woohoo!
Well, yes, sure. Okay, so this problem, by the way, has a name. It's called the baryogenesis problem, and it's actually considered one of the grand challenges in science. I mean, one of the 10 most important fundamental problems, perhaps, that physicists or scientists have yet to solve. So we think that studies of antihydrogen may help solve this quandary eventually. There are other things you could look for. Well, I mean, how do you look for specific things that antimatter might do, which hasn't been resolved? Well, everybody knows that apples fall towards Earths. And actually, everybody believes that an anti-apple would fall towards an anti-Earth. But nobody's quite certain about whether or not an anti-apple would fall towards Earth. Actually, people are pretty certain. There's a lot of indirect evidence that an anti-apple would fall towards Earth. But nobody has ever done the experiment of dropping an anti-apple and seeing which way it would go. There have been, up until very, very recently, has never been a measurement of gravity on antimatter. That's a direct free fall, Leaning Tower of Pisa type of experiment. So there are even people, though nobody really believes this, but there are even people who postulate that anti-apples would fall upwards rather than downwards. So that's one thing you could certainly look for if you were going to study antihydrogen, to see what happens when you drop an antihydrogen atom. Another thing that you could look for is spectral measurements. As you all know, atoms glow with characteristic colors. And so there's a big question, are the spectra of hydrogen and antihydrogen absolutely identical? So what do I mean by that? Well, going back to this pathetic model, we have electrons circulating around a proton, and the color that you get is basically proportional or inversely proportional to the frequency with which this electron circulates the proton. And the same thing is true for antihydrogen. It would emit light, it has a spectrum, and the color of the light, the wavelength of the light, has something to do with how fast the positron circulates around the antiproton. So could these colors be different? For them to be different, it would require that the positron in this pathetic model go around just a little bit faster. So the question is, could this actually happen? Now, there's an answer to that question. There's a very definite answer. There's something called CPT symmetry, which I'll get into exactly what CPT symmetry is a little bit later. But CPT in symmetry is one of the deepest principles that we know about how the universe actually works. And the spectra of hydrogen and antihydrogen could only be different if its CPT was violated, is not true. It's really very unlikely that CPT is ever broken, but if you were to do that, this would be an incredibly important discovery. It would be one of the most important discoveries in physics of the last 50 years if you could find something that breaks CPT. So why use antimatter to search for CPT violation? The reason why you might want to use antimatter is that we can compare the spectra of these two atoms in principle to extraordinary precision, to 1 part in 10 to the 18th. Think about that. What we're saying is that we could tell if this atom is going, this positron is going around just a little bit faster by 1 part in 10 to the 18th. Let me give you a visual image that might help you to understand what that number is. Remember those grains of rice that I had before in Angels and Demons? If you stacked grains of rice from here to the nearest star, that would be about 10 to the 18th. So this statement is equivalent to saying that if you removed 1 grain of rice in your stack from here to the nearest star, we could detect that. Obviously, we can't do it with grains of rice, but we can, in principle, with light. So this is an incredibly sensitive test of the CPT principle. So what is CPT? I'm sure many of you know this, but I'm going to go through this really quickly. CPT stands for, well, the individual letters stand for something that can be flipped. C stands for charge conjugation, P stands for parity conjugation, and T stands for time reversal. What do I mean by all of these things? Well, what I mean, actually I'll come to that in a minute, but what I mean is that if you do an experiment and you flip all 3 of these things and repeat the experiment, the results of the experiment have to be exactly identical if CPT holds, and every observation up to this date does show that CPT holds. So let me give you some examples. We know what happens if we have 2 positive charges. If I have 2 positive charges over here and I have my fingers on them and I let go, what happens? Freshman physics, right? They fly apart. So what happens instead if I take those 2 positive charges and flip their signs so that they turn into negative charges? If I do that and repeat the experiment, in other words, I had my fingers on these 2 negative charges and let them go, what happens? I observe exactly the same thing, as you all well know. So in CPT charge conjugation, sorry, I'm losing it here. In charge conjugation, what we mean is that when we take our experiment, everything that was positively charged, we make negatively charged, and everything that was negatively charged, we make positively charged. So that's charge conjugation. What about time reversal? Well, as you probably know, collisions are a very important topic in physics, and there are all sorts of physics collisions, but I'd like to show you a special sort of collision. This is something called a Newton's cradle. I'm sure you've all seen different versions of a Newton's cradle. The one in which you have about 4 or 5 balls and you let one ball go at the end and it bounces into the collection of balls and another ball floats from the other end. Everybody's seen that, right? How many people have seen this version of it? 2 people. So this does something absolutely spectacular, which you would never predict in advance. Well, I would never predict in advance. Perhaps some of you can. I'm going to let this go and just watch what happens. Fine. Look, every other shot, this comes to a dead stop. Who here thought that was going to happen? So anyway, we can predict what happens in this system. I'm going to stop this because it's distracting, but we could predict what happens in that system. I mean, it's nothing mystical or magical. Okay. So let me talk about the last symmetry in CPT symmetry. Well, actually, it's the middle one. It's the P, which stands for parity. Parity is just a fancy word for handedness. So I bicycle a lot. I have a pair of bike gloves. You know, I'm one of those. Have you ever heard the expression mammals? Middle-aged men in lycra. Anyway, I'm one of those, and so I have a pair of bike gloves. And so this is, of course, a left-handed glove, right? So the question about parity is there any way for me to turn this glove into a right-handed glove? In other words, is there some twisting machination to this glove that ever turns it into a right-handed glove? And the answer is no, unless you're sneaky. You can tell me the sneaky way of doing it? Yeah, if you turn it inside out, but that doesn't count, because that wouldn't be true if this was a solid object. You couldn't turn it inside out. There is no way to turn a left-handed glove into a right-handed glove except to hold it up in front of a mirror. And that changes left-handed into right-handed, as you all well know. So this parity, as it's called, is that there are left-handed and right-handed objects in the world. For those of you who've studied some chemistry or biology, for instance, you probably know that all of the sugars that we ingest in our life are, I believe, left-handed sugars, but maybe they're right-handed sugars. We, in fact, cannot digest the other sort of sugar. If it's a right-handed sugar, it just passes through our system and causes cramps and all sorts of things. But we don't get any nutrition from it. So parity conservation basically says that if we do an experiment and turn everything that's left-handed into something that's right-handed, we should get the same result of the experiment. Okay, I'm back online here, and as I was saying, with time reversal symmetry, what I can do is solve for the motion that you observed over there using the standard equations of freshman physics, conservation of momentum and conservation of energy. And that all works, but there's another way of looking at this. I actually have a movie that I made some time ago of this thing. You can see that movie. The advantage of the movie is it's got a clock, but once again you can see that the ball comes to a dead stop. The advantage of making a movie out of it is that I can run the movie backwards. I can reverse time. And if I reverse time, you'll see that nothing actually changes. So this movie at the top is the movie running in the forward direction, and this movie over here, you can see it starting at about 8 seconds or so, is going to run backwards. And if you watch these processes, you can't tell the difference in the experiment between the movie that has time running forwards and the movie that has time running backwards here. They'll just mimic each other, at least until friction gets in the way. So that's time reversal symmetry, and then skipping over what I was going to say about parity, to bring this to a close, summarize basically what CPT symmetry says is if I run an experiment one way, and then I change the charges of all of the particles, the handedness of the particles, and run one of the experiments backwards in time, and let's not go into how I run real experiments backwards in time. If I repeat that experiment, I'm going to get exactly the same result. And it turns out that this establishes without doubt, if this is true, that hydrogen and antihydrogen have exactly the same spectrum. So if we were to observe a difference, then CPT would have to be broken. Anyway, we can get a little bit more exotic for reasons why we might study antimatter. You know, the dark matter, dark energy problem is starting to get embarrassing. Actually, it's been embarrassing for a while. People have known about dark matter now for 25 years or so, and we have yet to observe any of it. And dark energy we've not known for quite so long. But at this point, physicists have lost 93% of the matter in the universe. Now, this is rather pathetic, really. And it's, well, let's just say it's rather pathetic. Now, chances are it's just that this is very hard to detect. But the last time we lost a significant particle, the neutrino, we found it pretty quickly. So the history says that this is a much harder problem, at least. But it turns out that it's easy enough to invent explanations that obviate the need for dark matter and dark energy altogether if you postulate that something is weird about antimatter. You can just get rid of them altogether. You don't need them to explain the observations that are out there. The problem with this is that this really, really quickly gets into crackpot territory, so maybe the less said about this, the better. But maybe, probably not. Okay, I've talked enough about the reasons for wanting to study antihydrogen. Now let's talk about how you actually would make antihydrogen. Actually, it's pretty simple, as it turns out. Many things are simple once you learn how to do it. But to just make antihydrogen atoms, all you need to do is to take several million positrons, cool them down, trap several tens of thousands of antiprotons and cool them down, and then figure out a way to gently mix the positrons with the antiprotons, creating antihydrogen. And that sort of just happens automatically. The harder step is to trap those antihydrogen atoms, because the traps have very, very little, they're very, very shallow. So it's easy to make antihydrogen, but it's very hard to get the antihydrogen to stick in the shallow trap. Perhaps some of you have played with those games that, you know, they used to be cheap plastic games which had little marbles and dimples that you had to roll the marbles into. That's the game that we're playing. It's really hard to get our antihydrogens into the dimples of our traps. But it has been done, and the first step, of course, is to make antihydrogen. And at this point, lots of antihydrogen was been made. It was first made by two collaborations, Athena, which no longer exists, and the A-Trap collaboration back in 2002. And hundreds of millions of antihydrogen atoms have been made to date. So quite a bit. If you were all to pack it together, it would be about 100 millionth of a gram, which would be, I'm afraid to even pick this thing up, but it would be enough to run this laser pointer for about 1 second if you annihilated all of the energy of all of the antihydrogen atoms that have been made so far. But still, that's really a microscopic quantity. It's only 100 nanometers on the side. Now, we would actually like to trap it, and to trap it requires a really rather complicated apparatus. This is a photo. You can't really see anything inside. So I'm going to just highlight just a very few aspects of what's inside of our actual trap. But first I'm going to talk about the real problem. I mentioned it a minute ago. Our traps have a depth of only about ½ Kelvin, or 40 microelectron volts. So, and antiprotons themselves are created with an energy of about 1 billion electron volts. So somehow or other, we have to take the antiprotons that we're ultimately planning to trap in the form of antihydrogen and cool them down by an enormous fraction. We have to cool them down by 14 orders of magnitude. Cool or select, I should say, them down by 14 orders of magnitude. That's a really long way to go. And if there are any, I always like to include this next little tidbit to annoy the particle physicists. The LHC only increases its energy of protons by a mere 8 orders of magnitude. We're cooling by 6 orders of magnitude more than the LHC increases their energy. This is totally meaningless, but it's kind of a fun thing to say. What's more relevant is that we use plasmas to make our antihydrogen. And the plasmas have an electrostatic potential across them, which is on the order of 1 eV or so. which means that our trap depth, the thing that we're trying to roll these antihydrogen atoms into, is something like 10 to the third to 10 to the fifth times shallower than the sort of potentials inside of our plasmas, which makes the whole thing very, very tricky. Okay, how do we do this? Well, first of all, we have to make bottles for antimatter. And who can tell me what the problem with making a bottle for antimatter is? You can't use matter to do that. You have to get rid of all of the matter because the antimatter will annihilate on it. That means that you have to evacuate your trap down to a vacuum, which is much better than people typically use in a lab. We get down to 10 to the 14th to 10 to the minus 15, 10 to the minus 14 to 10 to the minus 15 torr. And we can only do this by putting this inside of a cryogenic environment, which is about 4 Kelvin. But then, of course, the bottle itself can't have sides, which are materials. So we have to use magnetic and electric fields to make our bottles. So how do we do that? Well, I have a demo here which kind of illustrates this, but it may or may not be running. Let's see if it's running now. It isn't. So I'm going to just show you a movie of this demo. What this is it's an electron gun, which makes electrons. And electrons are very closely related to the positrons that we ultimately trap. They're just have the opposite sign. It makes a beam of electrons which shoots out in this direction in this tube. And you can see that beam because this tube is not very well evacuated. So there's gas inside here and makes the gas glow. Surrounding this device, there are some magnetic field coils. And I'll show you what I can do with those magnetic field coils in this movie. I'm just going to run the movie.
Oh, do you want it darker for the movie? Or?
Yeah, maybe, sure. What you can see this beam. The magnetic field is now off in this picture, so the beam of electrons just comes out straight. But as I turn on the magnetic field, which I hope, yes, what happens is that the magnetic field causes that beam of electrons to start going in a circle. And eventually the beam of electrons comes back, and it comes back to where they were born in the first place. So if somehow we had a method of getting electrons into this device without having the source down here where they crash and get absorbed, then we would have trapped those electrons because they would be just going around in a circle due to the magnetic field. So that's what we use. We use devices called Penning-Malmberg traps to trap both our antiprotons, p-bars is just the jargon term for antiprotons, and our positrons. And the way these things work is, let's consider the positrons first. They're of course positively charged, so we can bias these cylinders over here in such a way that this is very, very positive on this side and this side compared to the center region. That makes an axial electrostatic well, and the positrons can't go out in either direction from that well. They can, of course, go out radially, but we use a strong magnetic field, to confine them from going out radially, just like we use the magnetic field here to confine the particles radially. And then we can make a similar well with the opposite sign nearby for our antiprotons, and this allows us to make antiproton clouds and positron clouds, which are essentially adjacent to each other. These are actually not clouds, they're actually plasmas. Most plasmas are thought to be charge neutral, but it turns out that that is not an absolute requirement for a plasma. You can have charged plasmas, and these are very much charged plasmas. So in fact, most of what we actually do to make antihydrogen turns out to be plasma physics manipulations. I don't really have time to go into them in any great detail, but for instance, we had to learn, these are actual pictures of antiprotons, we had to learn how to compress our antiproton plasmas. We had to learn how to cool them down from hot temperatures to much lower temperatures. We had to avoid, this is a fascinating set of pictures, a little bit hard to explain, but we have to avoid something called centrifugal separation. The whole clouds are spinning and antiprotons weigh more, so they tend to want to go out toward the outside. And that's what you see here, except that our imaging system is such that the antiprotons these over here, image in a different place than the positrons. So this ring is actually surrounding the outside boundary of this cloud of positrons. Did I say that right? So these are positrons and these are antiprotons. How do I know? Years of experience. Okay, so we'd have to do a lot of that. But the trickiest of these plasma manipulations is how we eventually get these antiprotons to merge with the positrons. If we can do this successfully, we'll make antihydrogen. Yes?
Is there some significance to the fact that the antiprotons are smaller? Does that mean they're confined in a smaller region? Because they weigh more. So why are they
There are typically in our experiments far fewer of them, but I didn't mean very much by making this much smaller. We actually try to get the radii of these clouds to be about the same. They're actually, these are false depictions of what they look like. They're actually needles. They're about 3 centimeters long, and they have a radius that's typically about 3/4 of a millimeter. So they really look like a needle of plasma. Okay, but somehow or other we have to get these two things to merge together with each other. And, oh, well, how could we do that? We could just tilt them. Okay. And you could do that electrostatically, and in fact, that's how people did it for a long time. But that turns out to be a very bad way of mixing them together. It ends up, if you do it that way, that you wind up with far more energy in the antiprotons than you would want. So we developed a different method, which is based on nonlinear dynamics, and I'd like to go over that with you briefly. You've all seen a pendulum before in life, right? Start the pendulum going, it goes back and forth. You studied this endlessly in your freshman physics classes, where you learned that if you drive the pendulum at its resonant frequency, the amplitude of the pendulum will get larger and larger. Like many things that you learned in freshman physics, this is a complete lie. This is not what happens. Here's a computer model of what actually happens to a pendulum if you drive it at its resonant frequency. Just as you were taught, the amplitude of the pendulum gets larger and larger. But then something strange happens. The amplitude stops growing and actually starts to beat down all the way down to 0, and the pendulum actually comes to a complete stop, after which point the amplitude of the pendulum starts to increase again. Why does this happen? It happens because, just like your freshman physics instructors were liars, I'm sort of a liar too, this is not a simple harmonic oscillator. This is a nonlinear oscillator. And the frequency at which it oscillates back and forth is only constant if the size of the oscillations are small. When the pendulum starts to go over the top, the frequency slows down dramatically. You all know that if I swing my hand and have it go over the top, it's very natural for me to really slow down when I get to the top. So what happens at this point is that the drive frequency becomes out of phase, actually, with what the motion is, and the drive frequency starts breaking the motion and beats it all the way down to 0 until it stops. Well then, how do you get a pendulum up to high amplitude? I mean, I can do that with my hand without any trouble. You know, I just swing it in the right fashion, eventually it goes over. But all of you who've had kids have had spent endless hours actually doing this if you've been pushing a kid on a swing. A swing is a nice nonlinear oscillator, it's a nice nonlinear pendulum. And while you were probably unaware of it, what you're actually doing is timing your pushes to meet up with the period of the pendulum. So the higher the kid gets on the pendulum, on the swing, the less frequently you are pushing them. We do this completely subconsciously and naturally, and it, of course, works. But what do you do in a case where you can't use that sort of feedback? The only reason why that works is you can see the kid on the swing. Normally they're screaming, for instance, so you can hear them too. But you can see them, so you can time your pushes. What do you do when you're in a situation where you can't actually see them? Is there a way that you can get them to go over the top, which would, of course, result in really bad screaming, but never mind that. It turns out that there is. There's a process called autoresonance that will work for you. without any feedback. What you do is instead of driving the pendulum with a fixed frequency, you start with a frequency which is higher than the linear resonant frequency, and I've got another computer simulation of that. So initially, I'm starting with a drive frequency which is 1.33 now. You can see it's slowly decreasing. The linear resonant frequency of this pendulum is 1, and at time t equals 0, the drive frequency will get all the way down to that linear resonant frequency. But so far, nothing much has happened as you would expect because we're not at resonance. As we approach the resonance point, the amplitude of the pendulum starts to increase. Still not a surprise. But what is surprising is that as we go further and further, having the drive frequency continue to diminish slowly, the amplitude of the pendulum will just grow without bound, eventually causing it to go over the top. And if you look at it here closely, you can see that the drive frequency is actually matching the instantaneous nonlinear frequency of this resonator. This just happens automatically until the pendulum goes over the top, which breaks the whole phenomenon. Now, there are a couple of wiggles, but I think it will go over in just a minute. No. Couple of wiggles, and there it went over the top. So autoresonance is a general nonlinear phenomenon. It happens in driven nonlinear high Q oscillators, and it's sort of magical. It says that a nonlinear oscillator will, under some circumstances, automatically adjust its amplitudes so that its nonlinear frequency matches its drive frequency. And it has now been observed in a very wide variety of systems, astrophysical systems, solid-state systems. And it's very useful, and it turns out that we can use this to finesse our particles into, finesse our antiprotons into our positrons. And here's some data showing you that, but I'm really running out of time, so I should not go over that too much more. The last question about how we trap antihydrogen that I'd like to talk about is how we actually trap the antihydrogen. This sort of system works really well for electrons, positrons, antiprotons because they're charged particles. But antihydrogen atoms are not charged particles, and it wouldn't work at all. So what do? It turns out that antihydrogen, like hydrogen, has a small magnetic moment. It's like a small magnet. And we can take advantage of that because magnets can be trapped in a magnetic field that has a minimum. So here's a demo showing you this. Here's a mapping of a bathtub of magnetic fields so that the magnetic field is lowest in the center and increases in all directions to the outside. And if I allow let a particle go in there, a magnet, such that that magnet can't flip, then it turns out to be trapped in the field. It will stay in the field forever. Now, how do you make a magnetic minimum? By paying Brookhaven National Lab about $500,000, they will construct a magnet for you called an octopole magnet, which has the properties that it has a minimum at the center and the field increases in all directions as you go away from the center. These are very state-of-the-art magnets. They're quite strong. But let me give you another demonstration of how this actually works. I have something here. It's a toy, which unfortunately one of my colleagues lost all of the parts, so I can't really show you it in action. But I do have a movie of how it actually works. This has got a base which has a very strong magnet in it. And this is magnetic, so it really wants to drop to here. And of course, you have north poles and attracting south poles and things like that. So let's say, and this is a top. And let's say I orient this thing spin over this magnet with the poles, say north and the north pole, like this. Well, it's going to be levitated upwards, right? But that's actually not what's going to happen if I actually did this, because it would just flip and spin, and then the north pole would be attracted to the south pole and it would go crashing in. But if I spin this thing, then it has angular momentum, and then it can't flip, right? And if it can't flip, it can just float on top. And this is a great demonstration. It actually it's very finicky. But I have an actual movie of this from somebody who set it up. It's a slightly different version of the toy, but you can see there's the top, there's the magnetic base. The guy starts it spinning. He lifts it up and takes the plate away, and it just will sit there and float. It's really spectacular. It will float for 5 to 10 minutes on top there. And I wish I could show this to you, but never mind. So what does this have to do with our atoms? Well, our atoms are spinning. They have a spin. And they cannot flip spontaneously. So they float in our magnetic field in just the same fashion, well, crudely the same fashion as this top spins over this magnet over here. They're always oriented so that you have a north pole headed towards a north pole, no matter which direction you go in. And that's how we trap things. So how much have we trapped? Well, 2009 we had trapped 6 atoms. And we weren't even prepared to say that they were 6. In retrospect, there were. But the next year, in 2010, we published that we had trapped 38 of these atoms for the grand time of about 1/6 of a second. Not so fascinating. But 2 months later, we had trapped over 300 of these atoms and kept some of them around for 1,000 seconds. This being CERN, coffee is one of the most important things in the day. This is long enough to go from our lab over to the cafeteria, get a cup of coffee, and come back. In fact, we could have kept them around for longer, but it's just boring to keep them around for longer. So at that point, we flipped the switch and turned them off and generated some new ones. So what have we done with this? And I see I'm really running out of time. So really, really quickly, we have done some spectral measurements, not of the color at which they glow, but remember these things are spinning? If you send in microwaves at the right frequency, you can cause their spins to flip. And if you do that, they'll no longer be in these low field seeking states. You'll get exactly what you get here when it flips. It will go crashing into the sides where it will annihilate. And you can measure the frequency at which the microwaves have to be to induce the spin flip. This is a spectral measurement, which we've been able to do to about 1%. The accuracy of this measurement actually isn't in the microwave frequency, it's in measuring what the magnetic field is, because you can see that this is very dependent on what the magnetic field is. A better measurement, which we plan to do in the future, is to go between these 2 states in the atom. That leads to a measurement of the hyperfine constant for antimatter and would be a very interesting thing to do. We've done some very crude gravity measurements. I don't think I have time to discuss the data over here, but let's just say that if antihydrogen atoms accelerated in the field of gravity either upwards or downwards 100 times faster than normal matter, then we would have been able to detect that. Big deal. You really wouldn't expect them to fall up or down 100 times faster than normal matter. But the big deal is that this had never been done before in a free fall experiment and leads us in the direction to actually doing a proper measurement, first to see whether or not they go up or down with G, and then to do a more precision measurement. And finally, we have done one precision measurement. We've measured the charge of antihydrogen. The charge of antihydrogen is obviously 0. Nonetheless, it's not something that's been measured. And the charge, by the way, of normal matter is known to exquisite precision. Hydrogen itself has not been measured, but helium has been measured, and things like SF6 and I think H2 to something like 21 orders of magnitude, it's known to be 0. But in fact, the charges of positrons and antiprotons aren't individually all that well known. And so we were able to measure the charge of antihydrogen to 10 parts per billion, and that's actually slightly better than you would get from the individual measurements of positrons and antiprotons together. So this is our first precision, if you will, measurement on antihydrogen. So these are the 3 measurements we've done so far. Where are we going? Well, with help from a very unusual funding source, the Carlsberg Beer Foundation, We've put together a new experiment which is much better in many different ways. That's just coming online because CERN was shut down for a year for the LHC upgrade, and we hope to do better experiments then. We've applied for funding to do a better gravitational measurement, but we don't yet have that funding. And we're not the only people in this game. We think we're the best people, but Alpha, my collaboration, has studied all aspects of antihydrogen. We've trapped over 500 antiatoms, measured their spectral measurements, 1%, crude gravity, precision charge. There's another collaboration that's interested in spectral measurements of antihydrogen, and they've trapped perhaps a few antihydrogen atoms with actually a very low signal to noise. We have great signal to noise. As Akusa is interested, a third collaboration is interested in microwave spectral measurements of antihydrogen, and they've created a beam of antihydrogen atoms. And then there are two experiments that are interested in gravity, which have been approved at CERN. AGIS has actually gotten as far as trapping antiprotons, and GBAR, the other and last experiment, is still in the design stage. Well, that's all I wanted to say today. It's a great group of people. We have some pretty photographs of various pieces of apparatus. I hope you've learned something. Thank you.
It's 5 o'clock, so if you have another class or a commitment, please leave quietly. For the rest of us, we'll continue on with the question session that will last at least 10 minutes or so.
Yes.
Once you make the antimatter, what do you do with it?
I'm sorry?
Once the antimatter is made in the lab, what do you do?
Well, we make it and then it's stored in our traps, and then that's when we do things like the spectral measurements on it, or the gravity measurements on it. But we don't have any plans to send it someplace else or store it up. We don't really make enough of it to make that worthwhile. So these are physics experiments with the intention of studying fundamental properties of matter, not experiments that are going to lead to bombs or rocket ships, unfortunately. But
I was thinking maybe you just ate something somewhere in the lab.
I'm sorry?
It doesn't just neutralize in the lab.
Can understand.
Neutralize it by
No, I mean,
What happens when you flip the switch off?
Can you hear it annihilate?
these are, by particle physics standards, these are cheap experiments, but they're not cheap experiments. To detect the annihilations, we have a particle detector which costs about £1 million. It was made in England. So we can detect an annihilation with essentially 60% efficiency. So we can detect it with our detector quite well, but you certainly can't see it. It's an infinitesimal amount of energy.
At 511 MeV.
I'm sorry?
At 511 MeV.
Well, those are the positrons, but it's the antiprotons. What happens is the antiprotons turn into pions. The pions come cruising through our detector, and eventually they get eaten up as well. Now, as for how long we could keep them there, as I said, we only kept them there for actually we had one that we kept for 2,000 seconds, but it's really kind of boring. We don't, at the moment, have a way of detecting that they're in the trap, except by turning off the trap.
They were there.
So we can tell, yes, we can tell that they were there. Actually, think about it. For those of you who do experiments, you know that the residual vacuum inside of your trap is primarily consists of hydrogen if you have a good trap. And so we have one couple antihydrogen atoms inside of our trap, and we have exquisite vacuums, 10 minus 14, 15, something like that. But there's still, because the trap is big, a lot of hydrogen inside of our trap, on the order of 100,000 atoms. So if we were looking for the spectral properties just by shining in the light and seeing photons that came back out, and we know that the spectral properties of hydrogen are very likely very, very close to the spectral properties of antihydrogen, how are we supposed to see the spectral lines from the 1 or 2 antihydrogen atoms in our experiment compared to the 100,000 that are of hydrogen atoms, did I say that correctly, in our trap. So the signature that we actually use is annihilation, because normal matter doesn't annihilate, and that's what gives us this great signal to noise of about 500 or so. So what we do is we do something that causes annihilations to happen, and that we can detect. So there's really no point to us keeping the atoms around for a very long time. What would ultimately limit the lifetime of the atoms in the trap actually is that background. The trap is perfect. They won't escape it. But eventually they will run, the antihydrogen atoms will run into a normal atom of hydrogen and annihilate. And that's one thing that our competitors, A-trap, are better at than we are. They say that their vacuums are at the 10 to the minus 18 Torr level, for those of you who know these units. We're content at 10 to the minus 14 because it gives us lifetimes of several hours in principle. But that's what would ultimately happen. Yes?
So if I were to make, hypothetically, a more complicated element, so just say I had anti-helium, would the neutrons in that be exactly the same as normal neutrons that you just find anywhere else, right?
No, they would be antineutrons.
Okay.
And
so you
people
didn't mention those, so I was just going to...
Yes. People actually have made anti-helium nuclei and anti-deuterium and anti-tritium. It turns out that, remember I was talking about the economics 1 in a million? Every time you add another species in there, you get a multiplicative factor of about 1,000,000. So if you want to go from hydrogen, an antiproton, to deuterium, an antiproton and an antineutron, the chance of making that in a collision goes down by some factor of about 1,000,000 over what we've had. It becomes negligibly small. At this point, I would say that there is no prospect for making anything other than antihydrogen. Now, of course, we could take 2 antihydrogen atoms and fuse them together, except that that's normally done with deuterium and tritium, not with hydrogen itself. But in principle, we could do that. In practice, we can't, because the volume in which these antihydrogen atoms are contained is about this long and about this wide. It's a cylinder like that. So even if we put 2 antihydrogen atoms in the same space, they would never find each other. And in any case, if fusion was easy, we wouldn't have an energy crisis. So that's not a good route.
So also usually charge is the thing that we say is the difference. You know, an antiproton is just a proton but with a different charge. So an antineutron, without the charge difference, what's the differentiating factor?
So I'm a lousy plasma physicist, so I'm wandering off the edge of my diving board at this point. But the difference is the quarks. A neutron is made up of a certain set of quarks, and the quarks turn into antiquarks inside. As far as I know, nobody has ever trapped an antineutron. They've been made, certainly. And you can trap neutrons, actually, in a trap that's very much like our magnetic minimum trap. But I don't think there's any prospect for trapping an antineutron because since they're not charged, there's no easy way to confine them and cool them down. We at least can use the charge of the antiproton to confine it as we cool them down to more reasonable temperatures.
Dr. Fajans, it's the one part that you didn't have time for, but can you give us a mental picture? I think you were going through the nonlinear system to tell us about how you're going to bring those 2 needles together. And so could you take us through a little bit more on that way that you're going to bring the needles together?
Okay, sure. As I said, we use autoresonance to do this, and where was that? So, well, let me go back just a little further. So what we do is we have a potential well here and a potential well here. They're both trapped inside of their respective potential wells. But we start oscillating this cylinder, which starts pushing these antiprotons back and forth in that potential well. So they're going back and forth like this. And that's a nonlinear oscillator system because the well is not a parabola, it's got sides, so it's a soft nonlinear oscillator for those of you who know the jargon. And what happens is it's exactly the same way as the pendulum, that the oscillation gets larger and larger as we decrease the drive frequency over here. And eventually we can get it to go over the top, just as I did with the pendulum. but in a very gentle, finessed fashion. So here's some data showing what actually happens. We start out with an antiproton cloud, which is centered around, with an energy distribution centered around 0 eV, and we start sweeping a frequency downwards from somewhere about here, above it, the linear oscillation frequency of the antiprotons in the well. As we go down, what happens is that the nonlinear frequency of the oscillations follows this blue curve over here. And as we go down in frequency, what happens to the distribution is that it gets lifted up, just matching that. So here's what happens when we've shifted the frequency down from the linear frequency down to about 0.95. You can see that this is actually a measured distribution of the antiprotons. They sit here. We go further down in frequency. They sit up here. Finally, up there, we go up there. But and we can get it to go over the top. But this is not an easy thing to do, actually. We spent months of time optimizing this process. And months of time on an accelerator facility are very precious. So this really is a high priority thing for us, which is very difficult to do. But we'd like to do it much better. Yes?
Can I ask you 2 questions? So first, do you have a feel for how efficient you are in making sure that every antiproton makes an antihydrogen?
Okay, so there are 2 questions there, if I can expand it. How efficient are we making antihydrogen atoms? And the answer to that is very efficient. That if we start with about 20,000 antiprotons, which is typical in our cycle, we'll make about 10,000 antihydrogen atoms. So that's very efficient. These cycles, these plasma manipulations that get us to that point, take about 10 minutes. Think about that for a second. If you're familiar at all with fusion energy, it costs $1 billion to make a fusion energy device that keeps the plasma around for about a second or 2. And we keep our plasmas around for minutes, hours, sometimes. So we're very efficient at making antihydrogen atoms. We're very inefficient at making antihydrogen atoms whose energy is low enough for us to trap. We're actually relying, we never get any place close to the trapping depth. What we're relying on the fact is that we get a Gaussian Maxwell-Boltzmann distribution of energies of the antihydrogen that we generate, and just a few of them have the half a Kelvin or so energy that's necessary for us to trap them. The average energy of the antihydrogen atoms is probably about 40 Kelvin, and if you work out the math, you'll find in the Maxwell-Boltzmann distribution that about 1 antihydrogen atom on average has energy low enough to be trapped. And in fact, that's where we're at. So obviously our goals are to try and generate antihydrogen with a lower energy, get this process to work even better, or some other process to work even better so that we can trap more antihydrogen. 1 is adequate to do, 1 per 15 minutes or so, 10 minutes, 15 minutes is adequate to do some sorts of experiments. But 10 or 100 would make experiments that take months be doable in a day because it becomes a statistics game. So you had a second question.
My second question was, years and years ago in the late 80s and the early 90s, there were a lot of papers that came out of CERN that measured gravitational trajectories of protons and compared them with those with gravitational trajectories of antiprotons. Is your gravitational sensitivity yet better than theirs was, or do you even know what I'm talking about?
I don't know what you're talking about, which is not to say the way people normally say that. Certainly people have measured things like the tidal forces on the Earth.
These were experiments out of the UA1 beam, I think, where they were just cooling proton and watching the trajectories as they went through, I think, wire chambers or something like that.
Okay.
And antiprotons through similar devices.
I could be wrong, but actually what I think they were measuring was not the trajectories of the individual antiprotons, but the trajectory of what happens to the machines themselves as the tidal forces from the moon combine. I could be wrong, about that, but gravity is incredibly weak, and I don't see.
They didn't have very good results, but there was a preprint stream that was coming out. Okay.
I know the guy to talk to, Bob Jacobson, because he's the guy who measured the tidal forces on the CERN ring. But I'm pretty sure that it was not on the particles themselves. The energy, I mean, when you think about it, you can barely bend the antiprotons in the ring with very strong magnets. So how is gravity going to work on that?
It's a really cool experiment. I don't remember the details.
Sure.
Though.
But certainly the ring itself shifts with gravity and the tides. And that's what I'm familiar with. Yes?
Yes, as you're trapping the two particles, they form this antihydrogen. What happens to the Coulomb interaction when distance gets really small, close enough? Either just going to collapse the two particles to, right away, annihilate the two particles, or you can still have this for 1,000 seconds. How do you really get the two particles, just like the regular matter, the electron orbiting around this proton? What happened to the Coulomb interaction here?
Well, of course, an antiproton doesn't annihilate on a positron. It only annihilates, for that matter, an antiproton does not annihilate an electron. So we actually use a good bit of sympathetic cooling where we cool an electron plasma and put our antiprotons into that electron plasma to cool the antiprotons down. And there, the Coulomb interactions don't matter because it's perfectly acceptable for an antiproton to get as close as possible to a positron. Nothing's going to happen, they don't annihilate. But I'm not actually sure I fully understand your question. The process that leads to the creation of antihydrogen is thought to be, without any strong proof, three-body recombination. So what happens when we manage to mix these two species together, we have an antiproton. There are two positrons that are nearby. One of the positrons gets trapped into a very high Rydberg state, about n equals 40, 50 or something like that, while the other positron gets kicked out of the system. In fact, when I said we've made hundreds of millions of these antihydrogen atoms, though not trapped them, obviously, what we've made is 100 millions of Rydberg atoms in the n equals 40 state, but they're incredibly weird Rydberg atoms. I actually have another movie and a different presentation of that, but what happens is you have a positive charge in the center and a positron orbiting around it, but there's also a strong magnetic field always present in these systems. So let's say the strong magnetic field is oriented out of the board like that. This is an antiproton, so it's minus charge. Sorry about that. What happens is that initially in these n equals 40, 50 states, the motion is actually, of the positrons is actually dominated not by the antiproton but by cyclotron motion. So it does that. And then on top of that, there's what is called, since there's an electric field like this, the other way, and a magnetic field like that, you get what's called an E cross B drift motion. And so what happens is the positron circles like this, doing cyclotron orbits, but E cross B drifting at a frequency which is set by the E cross B drift motion around. And then if I look at this longitudinally so that the magnetic field is going like that, so, here's the antiproton in the center. What the positron does is bounce back and forth in the electrostatic well, which is created by this antiproton, as it circles around, I can't draw this very well, but as it circles around the proton. This is a completely classical atom initially. And then what happens is it starts to radiate some of its energy away. By the time it gets down to n equals 20 or so, that radiation process is quite fast. So there's a time which we think is on the order of half a second for 99% of them to decay down from the n equals 40, 50 states in which they're born down to the n equals, the ground state where we'd like to study their properties. But this is a little mysterious to us. If we had listened to theorists, we would never have done these experiments because they're impossible. Couldn't possibly work. And one of the reasons why they couldn't possibly work is that during this cooling down process, the theorists all said that there would be spin flips. And they would go from low field seekers to high field seekers to low field seekers, except as soon as they turn into high field seekers, we would lose them. Apparently that doesn't happen. Well, that's all we can say.
Let's thank our speakers.